Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the isochoric process. All the details about isochoric process. So first of all, let us discuss that what is isochoric process. So in isochoric process, volume remains constant. When a gas goes through an isochoric process, then its volume remains constant. There is a simple example of this condition in a gas. You can imagine a piston which is being fixed at its position, and there is a cylinder in which this piston is fitted, and this piston is not allowed to move in any direction. So we can say that this piston is fixed, and this process in which gas is heated, let us heat the gas. Let us first of all draw the diagram. This is a cylinder containing an ideal gas, and piston is rigid piston, which means that it would not move. So when we will heat this gas, the piston will not move and volume will remain constant. Now let us see that if volume remains constant, then according to PV is equal to nRT, P by T is constant. So this is obviously, you know, that this is Gay-Lussac law. So gas obeys Gay-Lussac law in isochoric process, and we can say that P1 by T1 is equal to P2 by T2. Okay. Now if we draw the PV diagram of isochoric process, then its PV diagram would be a straight line parallel to the pressure axis, and therefore you can say that slope of this line, slope is dP by dV, will be equal to infinity, because you can see that the angle of this line with x-axis is 90 degree, so the slope of this line is infinity. And if we talk about the bulk modulus, this is bulk modulus. So bulk modulus beta will be minus dP by dV by V, and this you can find in the solids elasticity part about the bulk modulus. So bulk modulus is dP minus dP by dV by V. So again bulk modulus will also be infinity. And there is a term which is called as compressibility. This is 1 upon bulk modulus. So it is 0. Compressibility is 0, because obviously this gas cannot be compressed because it is going through isochoric process and its volume remains constant. Now if we find out the isochoric expansion coefficient, I am talking about the gamma, volumetric expansion coefficient, and we know that gamma is equal to delta V upon V delta T, and obviously if volume is constant, then delta V is 0. So if delta V is 0, then gamma will also be 0. So adiabatic isochoric volumetric expansion coefficient is 0. And if we talk about the example of this process, so we can say the first example is the fact that a gas which is filled in a cylinder and it is having a piston which is rigid, is the example of isochoric process if that gas is being heated. And we can also say that the melting of ice is a isochoric process, although we know that the density of ice and density of water is not same, which means that if m mass of water melts, m mass of ice melts, then the mass of water formed is same. But if v volume of ice melts, then the volume of water formed is quite is less by 9%, due to the fact that density of water is greater than 9% by density of ice. So, but we ignore this effect and we can say that this effect is negligible, and hence we can say that isochoric process is melting of ice. Okay, but more precisely we can deny the fact that melting of ice is isochoric process. So this is now we also know that the molar specific heat in isochoric process is Cv. So molar specific heat is Cv, and gram specific heat is Cv upon molecular mass of the gas, and Cv we know is R by 2 into F, where F is the degree of freedom. So Fr by 2 is the molar specific heat. Now work done by the gas or on the gas, work done by or on the gas in isochoric process is 0, because delta V is 0. So there is no work done by the gas or on the gas. And if we write down the heat supplied, so all the heat supplied to the gas goes in increasing the internal kinetic energy of the gas. So this is internal kinetic energy of the gas, but this is for real gases. Okay, so this is obviously for the real gases, but for in fact this is for ideal gases, and we just need to talk about the ideal gases. So any heat supplied to an ideal gas going through isochoric process is utilized completely in increasing the temperature of the gas and in increasing the internal kinetic energy of the gas. So dq is equal to du. Okay, now let us discuss about the value of so isochoric process I think was that's it, and now let's move on the next process, which is isobaric process. So in isobaric process, let us see that pressure is constant. So pressure is constant, and the gas obeys Charles' law, V by T is constant, and we can say that V1 by T1 is equal to V2 by T2. This is the Charles' law. The gas, the slope of the PV graph is 0. Slope is 0. Slope is dP by dV, and this slope is 0, and bulk modulus, which is minus dP by dV by V, is also 0. This is bulk modulus. And compressibility is 1 upon bulk modulus. So compressibility, we can say that it is infinite, and the work done in isobaric process is equal to P delta V, where P is constant and delta V is change in volume. And we also know that PV is equal to nRT, and when pressure is constant, P delta V will be equal to nR delta T. Okay, so work done in isobaric process can also be written as nR delta T. This is the work done in isobaric process. Now if we discuss about the molar specific heat, yes, molar specific heat. So molar specific heat for isobaric process is Cp, and Cp is obviously we know that it is F by 2 plus 1 into R. So we can find out the value of Cp for different values of degrees of freedom. And the heat supplied to the gas in isobaric process is utilized into two parts, which is partially in increasing the temperature or the internal kinetic energy of the gas, and partially in doing the work against the surroundings. So this is the heat supplied to the gas, which is utilized into two parts. The example of this isobaric process can be a piston having a gas enclosed in a cylinder, and it is being heated, and this piston is moving slowly in the upward direction. So if this piston is moving slowly in the upward direction, then we can say that net force on piston is 0, and the force on the piston from the atmosphere is equal to the pressure of the gas. In fact, pressure of atmosphere is equal to the pressure of gas, and we know that pressure of atmosphere is constant throughout. So we can say that in the complete movement of this piston, this gas has a constant pressure, and we can say that this is a isobaric process. Naturally, we can say that any process in which let's suppose boiling of water. So boiling of water occurs at a constant pressure of 1 atm. So boiling is a example of isobaric process. So this was, and we can also find out the gamma for isobaric process. Gamma was this is not Cp by Cv, this is delta V by V delta T, which is volumetric expansion coefficient. So we can say that if P is constant, then V is directly proportional to T. So V is equal to Ct. So dV is equal to C dt, and dV by V will be equal to dt by T, and dV by V by dt is equal to 1 by T. So gamma is coefficient of volumetric expansion. Coefficient of volumetric expansion. So this gamma is equal to 1 upon T for isobaric process. So this was the complete information about the isobaric process. Now let's move on the isothermal process. So this is an important process, and in this process temperature of the gas remains constant, and gas obeys Boyle's law. So P into V is equal to constant, and P is inversely proportional to V. So if we draw the PV graph for isothermal process, then it is a rectangular hyperbola. Okay, and if we talk about the slope, so slope is dp by dv, and we can find out the slope by differentiating the equation. So we know that pv is equal to constant. So if we differentiate both the sides, then it would be dp into v plus dv into p is equal to 0. So dp into v is equal to dv into p. So dp by dv will be equal to minus of, this is minus also, minus of p by v. So slope of this process, isothermal process, is minus p by v. Okay, and the bulk modulus. Now this isothermal process PV indicator diagram is also called as isotherm. So this is also called as isotherm. Okay, now bulk modulus is minus of dp by dv by v. So you can say that this bulk modulus is plus of pressure. So isothermal bulk modulus is equal to the pressure of the gas, and the compressibility, we know that the compressibility is equal to 1 upon bulk modulus, and therefore it is 1 upon pressure. Now we know that what is the du in this process. So du will be 0 because T is constant. So change in internal kinetic energy of the gas will be 0. We are talking about the real gases only. So any heat which is given to the system in this case will be utilized into work done only. And the specific heat C in this process, molar specific heat C in this process is obviously infinity, because we can say that Q is equal to NC delta T and C is equal to Q by N delta T. So if temperature is constant, then C will be infinity. This is molar specific heat. Now if we talk about the work done in this process, so work done can be calculated by integration. So we know that small work done dW will be P dV, but obviously P is variable in this case, and P is nRT by V, where T is constant. So dW will be equal to nRT into dV by V, integrating both the sides. So work done will be equal to nRT, limit of volume will be from V initial to V final. So nRT ln V final by V initial. This is the work done in isothermal process. Okay, and now if we discuss about the necessary conditions for isothermal process. So necessary conditions are two. First of all, let us discuss an example. Let us see that there is a piston which is enclosing a gas, ideal gas, and the walls of the container are initially adiabatic, which means that heat exchange is not allowed through the walls of the container. So just imagine that we are compressing the piston and we are compressing the gas. So by compressing the gas, more and more heat would be developed inside the gas, because the molecules will start to collide with each other, and due to that collision the heat developed will increase the temperature of the gas. So the volume, in fact the process would not be the isothermal process because temperature is not constant. So if we want the process to be isothermal, we need to dispose of that extra amount of heat which is being generated by the collisions of molecules. So for that, to dispose of that heat, we need that the walls of the container should be conducting. Because if the walls of the container are conducting, then that extra amount of heat would be thrown out to the atmosphere or the surroundings, and hence the temperature of the gas can remain constant. Now there is another thing which is very important to note. So first of all, the first necessary condition is that the walls of the container or system should be conducting. Now let us imagine a situation in which we suddenly compressed the gas. Okay, if we suddenly compressed this gas, then we would see that temperature will increase for some time, and then after, by releasing the heat, temperature could attain its initial value. But in that case, this process would not be the isothermal process, because in isothermal process the temperature must remain constant throughout the process. It is not that temperature may increase or decrease initially and then attains the original value back. So this is not isothermal process. In fact, in isothermal process, the temperature of the gas should remain constant throughout the process. So if we suddenly compress this piston, then for some time the temperature of the gas will increase. Then after releasing that extra amount of heat, the gas will attain its initial temperature again, but that would not be the condition for isothermal process. So for isothermal process, the process should occur very slowly, and in fact it should be a quasi static process. So for slow occurring process, there would be enough amount of time for the system to throw out or to dispose of the extra amount of heat simultaneously as it is being generated by compression. So as we will compress the gas, the extra amount of heat would be disposed of simultaneously, and the temperature of the gas will remain constant. So this is very important, that process should occur very slowly. Should occur very slowly. So this is these are the two necessary conditions for an isothermal process. Now let us discuss the gamma, which is the expansion coefficient. So gamma we know is again dV by V dt, and dt here is 0, so gamma in this case will be infinity. So this will be the gamma for an isothermal process. So this was enough in this video, and in the next video we'll be bringing the detailed analysis of adiabatic process. I have not clubbed that adiabatic process in this video because there is enough things to discuss in adiabatic process, and it would make this video a bit longer. So I'll be making another video or separate video for adiabatic process. Thank you.